Today we're going to be spending time counting what's called strings, we'll define that in a minute, with replacement. So for warm-up, what we did was spend some time looking at counting all the three-digit combinations that we could do, beginning with D, and we came up with this list here. Then, looking at this part here, many Star Wars droids are named beginning with a letter and a single digit. For example, R2, D2, and C3, PO. So we're just going to look at the two digits to begin with here. Sorry, not two digits, but the prefix, the R2, the C3. So how many different name prefixes are there? So, for example, Luke Skywalker will often say, oh, it's an R2 unit in my X-Wing. R2 unit means that that's kind of the category R2, and then there's D3, D4, or D, etc. So what we do is we count the number of letters. There are 26 of them. The number of numbers, the characters we have for a single digit, would be 0 to 9, so there's 10 of them. So 26 times 10 gives me 260. 260 prefix options. All right, so today's going to be a great day because we're going to talk about outfits, and we're going to talk about tests and license plates and playing the lottery, all those fun things. But we're going to start by talking about just numbers, counting them. We're not actually going to do much of probability, although the jump to probability is fairly quick. All we have to do is take the total, take what we're looking for and divide by the total. So let's look at this here. We're going to talk about what's called the multiplication counting principle, which is what you instinctively did up here. You multiplied the counts. There's 26 here, there's 10 here, and you multiplied the counts. And that's essentially what we're doing. So you have 3 pairs of pants and 5 shirts. And we will make a tree diagram to see how many possible outfits you can have. Then, how would this change, how would this scenario change if you included your 3 pairs of shoes? All right, so my tree diagram is going to look something like this. I'm going to start with the idea of my outfit. I'm going to choose a pair of pants, but notice I have exactly 3 to choose from. So I'm just going to call this pants 1, pants 2, and pants 3. All right, so now within each subcategory, and it might be a little bit hard for you to do this because I can zoom in and you can't, but within each subcategory, the pants, I can choose one of 5 shirts. So S1, that's an S, not a 5, S2, S3, S4, and S5. Now, it turns out I can do that for each one of these. S3, S4, and S5. And as you see, we're going to be running out of space pretty quickly. And if you do run out of space, that's fine. Just do ... That'll work fine. Ellipsis there. S3, S4, and S5. So if we consider how many total options we have, we can just follow the tree diagram. An outfit. I can do pants 1 and shirt 1. Or pants 1 and shirt 2, or pants 1 and shirt 3, all the way down the line until I get to pants 2, shirt 5. Your Hawaiian shirt, no doubt, there. So how do we count that? Well, how many options do I have in this first row? How many options in my first choice? How many options do I have? Right, I have 3 options. And then when we look here, how many options do I have in my second choice? Well, I clearly see that I have 5 options there. So in the end, I have 15 outfits that I can select based on these 2 categories. That is, only my choosing my trousers and then my shirt there. So now what do we do if I change the scenario? How would this change if you include 3 pairs of shoes? Well, I'm going to zoom in only on exactly 1, okay? And I have the option of zooming in really small, so you don't. So feel free to not do this on your diagram, or at least just do it once. So from the shirt 1, I can do a shoe 1, a shoe 2, and a shoe 3. which now changes my scenario from 15 options or 15 outfits. This now upgrades it from a 3 times a 5 to a 3 times a 5 times the shoes. So now I have 45 different outfit options. So all of this brings us to the multiplication counting principle. And it says this: let A and B be finite sets. Finite, of course, means they end. The number of ways to choose one element from A and one element from B is the number of A, the number of elements in the set, times the number of B. And that's it. So you just multiply things through. So let's look at an example of this in a lottery. You may have heard of lottery. That's where that's for people who can't really do math, and you just try to make a lot of money by not doing any effort. So that's lottery. So a lottery game played in some states involves picking 3 digits, 0 to 9, in order. And you can repeat these things, right? So for example, I could choose 000, and you don't have to write this down. 000. I could also choose 001, etc., all the way to 999. So I could choose all of those because order matters in this one. So I could choose 1, 2, 3. I could choose 6, 6, 5, 1. Any of those in between. So describe a sample space for this experiment. That's actually it there. And determine the number of elements in the sample space. Determine the number of elements in the sample space. My description, I started the pattern right here, 0, 0, 0, 0, 0, 1, all the way to 998, 999. That's my description of it. So how many do we have? Well, if we think about digits, let's call this 1 digit, this 2 digits, and this 3 digit, right? And I can put inside, I can put 0 to 9, 0 to 9, or 0 to 9. So I have 10 options here, 10 options here, and 10 options here. So what do we do? 10 times 10 times 10 is 1,000 elements. Sorry. Yep. In this sample space over here. So, strings. When elements in a set must be ordered, the list is called a string. The number of elements, or symbols, or characters, or however you want to call it, but usually we say elements in a set, in a string is called the length of the string. So let's look at a scenario where you're given a multiple choice test. And so you have 5 choices each, A, B, C, D, and E. On a multiple choice test, there are 22 questions. Let's say you randomly guessed, which is the next problem down here, randomly guessing. What's your chance of randomly getting it correct? Okay. How many possible completed answer sheets are there? So if we're having a hard time visualizing what's happening, just remember that the first option is A, all the way to A, and there's 22 of them, right? Then the next option is A, all the way to AB, and do that. Notice we call this one, still it's a string with replacement. Why? Because I can use the A as many times as I want. I can use A all 22 times. I can use B all 22 times. Okay? So that's why it's saying with replacement. It's because I don't extinguish my options just because I used it once. So what does that look like? Well, if I have 22 questions, this represents a question. I have 5 choices. And this represents a question. I have 5 choices. Boop, 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 boop. So how many choices total do I have? Well, using the multiplication, essentially what we're doing is 5 for the first question, 5 for the second question, all the way across the board. So it's 5 to the 22. So 5 to the 22 is a very large number. Equals, or I'm going to say approximate here, and I'm just going to write this in scientific notation so it's a little bit easier to read. It's about 2.38 times 10 to the 15. That is, so in case you wanted to know what this number is, it's 2.38 quadrillion options. That's a big number. Next, if you guess randomly on each question, for example, you put all A's down, or you're guessing ABC, ABC, ABCDE, ABCDE, what's the probability of answering all 22 questions correctly? So remember, there's only one answer over 2.3 quadrillion. And, I mean, how do you even write that as a percent? It's so small, it's pretty much zero. 0.00, and you have to have 16 of those, 4%. Oh, and then if you move it over 2, you get your percent. So it's so small, you might as well not do it. So, how would the answers in example number 2 change if there are only 8 questions? So now it's more of like a quiz rather than a test. So walk through it real quick with you and or your neighbor and see how those two things change. So if there's only 8 questions, we have 5 options, 5 to the 8th power. So this one I can actually write down. I don't need any special notation. 390,000. So not even 500,000. All right, and so now my odds are that. My odds are 1 over that. So that's approximately 0.123452256. So as we see, it's not percent, so it's a 0.00025%, which is still small, but heck, I take those odds compared to the other one. You might have noticed some patterns in Massachusetts about how numbers are delineated. In fact, I saw a massive trend in California that the first digits, for some reason, were 5s and 6s for all over the place in Southern California. But it turned out that the 4s and the 3s were up higher. So there is actually sometimes there's codes about the numbers about where counties you might live in. But in this one, there isn't necessarily. So in a certain state, license plates have 2 letters followed by 4 digits from 0 to 9. So how many license plates are possible? Well, 2 letters, so that's 26 in my first option, then 26 in my second option. Then after that, I have 10, and a 10, and a 10, and a 10. Now, it doesn't say you can leave it blank, so this is assuming not blank. If I could leave something blank, then I would have to put another one in each one of these, because then I could have these 2, and then 11th one would be blank, and then those guys there. So when we multiply this out, I'm going to get 6,760,000 different plates. Now in this one state allows either letters or digits for all 7 characters. So how many possible plates are there? If 4 new characters, for example, a hand, a heart, a plus, and a star are introduced, how many more options? And this one says more options, not total options. So this one you have to pay attention to when you're calculating. You're actually calculating the difference, or after you find the total. All right, and the last thing we're going to take a look at is called independent events. Independent events can be described as events which the probability of A does not affect the probability of B. So for example, choose cards and then you replace them after each pick. So let's read through the actual definition. Events A and B are independent if and only if. So there's a nice little if and only if there so that it becomes a biconditional. And so whenever we use the word if and only, there's the phrase if and only if, it means we have a definition. All right, so the probability of A intersect B is equal to the probability of A times the probability of B. So a good way to remember about this is that this is the and, that they're both happening. First one and then the other. First one and then the other. So let's see here. The spinner's shown, I have 1, 2, 3, 4, 5, and 6 on the spinner, just like on a die. So the spinner's shown is used in a game. If a person spins an even number and then a multiple of 3, they win a TI-85. So what are the chances of them winning? Well, notice that if I spin an even number to begin with, it doesn't change the probability of the next thing because a multiple of 3 and evens are they're independent from one to another. Because it's not like I spin and then because I got on the evens, I have to cross out all the evens. And then I have to determine the probability then. So let's see here. It's simply going to see, we're going to do the probability of even times the probability of multiple of 3. So I'm just using an abbreviation there, times 3, to represent that. So the probability of even, well, remember it's the even is the what I want over the total, and clearly we see that's 3 over 6, or 1/2. So the probability of even is 1/2. And we're going to multiply this by the probability of a multiple of 3. Well, I only have 2 multiples of 3 here. I have a 3 and a 6. So that means that's going to be 1/3. 1/3. That is 2 over 6. So when we multiply that, we have a 1 in 6 chance of it happening. A 1 in 6 chance of this happening. Or you can round it to be a little bit more than 16, or approximately 17%.